I'm sure you've seen the equation speed equals distance divided by time before. So we're going to have a little bit of a closer look at that now at GCSE. There are a couple of little bits we need to clear up, as well as the difference between speed and velocity. And then we're going to look at distance time graphs and their properties. So let's get into that. Okay, so here is the equation speed equals distance over time. It's a basic equation of physics. But one of the things to realise about this equation is that the distance moved is actually the total distance travelled, and the time taken is the overall time. So we're dealing with totals. Now I can walk 10 metres in 5 seconds, and that will give me my total distance and my overall time, but my speed might not be constant during that time. I might move a little faster to begin with and a little bit slower towards the end, and therefore all I can calculate knowing that overall data is actually the average speed. So that's the first important thing to realise, that this equation only gives the speed as an average over that particular distance and over that particular time. Here's the familiar symbol for it, speed equals distance over time. If you're talking about displacement rather than distance, then you can talk about average velocities, because obviously displacement is a vector and the direction is part of that, and therefore you would then get the velocity and the average velocity, because the difference between velocity and speed is that velocity is a vector and therefore it is speed in a particular given or stated direction. So here's an example of the difference. 3 meters per second is a speed, but 3 meters per second to the right is a velocity, because you're specifying that directional information as well, in addition to the actual magnitude of the speed. Okay, so here are a couple of questions. Nice easy questions, just using speed equals distance over time. Again, technically this should say the average speed of the lab trolley. So 3.2 divided by 1.9, I've got this here on my calculator just here, is 1.68. So the speed is equal to the distance, which is 3.2 meters, divided by the time, which is 1.9 seconds, gives us a speed of 1.68 meters per second to 3 significant figures. Technically, I suppose you should quote it to 2 significant figures, because that's what the data is. So let's round it up to 1.7 meters per second. This one here I'm not going to do get the answer to, although I think the answer is something like 4.7 if you want to have a go at it. But it says a ball rolls for a period of 3.2 seconds and travels 15 meters to the left. Now technically that's the displacement. Alright, so we can work out the average velocity using those numbers, 15 divided by 3.2. But if we want the velocity, we will need to say that the velocity is to the left. And then again, if it rolls in the opposite direction, its velocity will be whatever the answer to that is. I think it's 4.7 to the right in the opposite direction. Okay. Now let's look at how we can represent these quantities, speed, distance and time, on a graph. And the graph, I'm sure you've seen before, is a distance time graph. Time on the x-axis, distance, or even displacement as well, sometimes at GCSE, on the y-axis. And the particular shapes here of the different lines. So if you have a horizontal line, that's a stationary object, and a straight line that's not horizontal, so sloping, shows a constant speed or a constant velocity. The steeper it is, the faster it's going. Okay, getting the speed information, you can actually calculate the speed from a distance time graph, is all about knowing how to calculate a gradient. So let's have a look at how to do that and remind ourselves how to do that. So here is a graph on the left, and here is a graph on the right. The graph on the left is just an abstract graph like you might see in maths, and the theory of how to calculate the gradient we'll do on the left, and then we'll apply that to a distance time graph which we see on the right. So here's a line on each of them, could be the same line, and let's talk about how to calculate the gradient. So the gradient is calculated by working out the change in the y variable and dividing it by the change in the x variable. You might have seen it as delta y over delta x. You might have seen it as y2 minus y1 over x2 minus x1. All of those three things are equivalent. They all mean the same thing. They all mean take the change in the y variable and divide it by the change in the x variable. So let's say this is 10 and this is 5. We can show here that if it's coming from the origin, the change in the y variable is 10, it's gone up by 10, and the change in the x variable is 5, it's gone up by 5. So if we wanted to calculate the gradient of this on this particular example, that would be 10 minus 0 divided by 5 minus 0, or just 10 over 5. So the gradient of this graph is 2. Now that has no units because it's just an xy graph. But if we look at this one on the right, we can see that the units have physical significance. The y variable is distance and the x variable is time. So here, the gradient, which is the change in the y divided by the change in the x, because distance is y and time is x, we have the change, well, let's not write change, let's just write delta, because it means the same thing but it's shorter. The change in the distance divided by the change in the time. And now look what we've got distance over time being equal to the gradient. And as we know from our equation calculating speed in meters per second, we end up with the gradient being equal to the speed. The gradient is the speed, it represents the speed. So the slope of that line tells you how fast the object is going. So here, if we had the same data on our graph, 10 and 5, as we did on our abstract mathematical gradient calculating graph, we can show that the speed, not only the gradient, but also the speed, is equal to the change in distance, which is 10 minus 0, but I'm going to leave that out because it's just 0, divided by 5 minus 0, just 5, is equal to 2. But this time, it's 2 meters per second because the axes have units. Okay, so what we've learned from that is the gradient of a distance time graph is equal to the speed of the object. If it's a straight line, it's equal to the speed all the way through. But you know, this object could be moving at different speeds all the way through, going very, very fast and then stopping, blah, blah, blah. As long as it gets to the same point at the same time, and there's actually a nearly infinite speed there, look, it will have the same average speed. Okay, good. So let's just recap that with these. Here we've got a horizontal line, the gradient is 0. So when you're doing these, think, what's the gradient? Think about the gradient, that's the same as the speed. So this graph shows, I'm going to put in brackets, 0 gradient, and therefore no speed. Oops, sorry, no speed. i.e. the object is not moving at all. It's stationary. Second one here shows a constant speed. Okay, it's a constant speed. The gradient isn't changing, it's not 0, so there is a speed, but the speed is not changing because the gradient is not changing, it's a straight line. Okay, constant speed. This graph here shows also a constant speed, but because the distance is decreasing, technically this will be a displacement time graph because we can show that the object is moving in the opposite direction. It's moving from 10 meters from the origin back down to 0, whereas this one is going up to 10 meters, so it's going away from the origin. This one's going towards the origin with time, so it's going in the opposite direction. As soon as you bring in the word direction, that means you must be talking about velocities and displacements. So constant speed in the opposite, or sometimes called, or sometimes referred to as the backwards direction. It's going back towards where it came. And this graph is actually a curve. So this one you can see that the gradient is getting steeper and steeper, and so we can show that the speed is getting steeper and steeper, so we have an increasing speed, which we normally call an acceleration. Again, I'm mixing up the scalars and the vectors a little bit there. Okay, good. All right, so let's have a look at this one. Nice, easy question. calculate the speed of A. So A is this blue line here. So it goes from this point here, which is at the origin, to this point here. And this point here has coordinates 10 and 2. So looking at that, we can say that the speed is equal to the change in distance, which is 10, divided by the change in time, which is 2. So that's the same as our example before. I think we had 10 over 5 before. This one's 10 over 2. Okay, now with the red line of B, this is technically a displacement graph, this one, because it's coming back in the other direction. But let's just take the magnitudes of those things, and we'll look at the signs and how they come out of that as well. So I'm just going to do this final section here from this point here at 7 seconds to this point here at 10 seconds. Now we can see that at the beginning of that section at 7 seconds, the object, let's do this in a different colour actually, the object has a speed of 8 seconds, sorry, just a distance of 8 meters, and it moves back to 0. So it's travelled down 8 meters, so it's effectively gone minus 8 meters. In terms of the time, it started off at 7 seconds and it finished at 10 seconds. So it's gone for a duration of 3 seconds. So that's, in terms of the magnitude, that's 8 over 3. In terms of the actual vector quantity, the actual velocity, it's going to be minus 8 over 3. It only wants the speed here, so it's talking about the magnitude of it. So I'm going to ignore the negative sign. If it was asking for the velocity, I would include the negative sign. So the speed here is going to be 8 over 3. It's travelled a distance of 8 meters in the opposite direction, obviously backwards, returning to the start, which is going to be 2.67 or 2.7 probably, you would round it to meters per second. Okay, and that's that.